Hello, everyone, and welcome back to Learning with Jelly. Today is part 2 of Bayes' Theorem. So we're going to cover Bayes' Theorem as it pertains to diagnostic testing. If you did not see part 1 of Bayes' Theorem, in which I break down the formula, please go back and view part 1. But let's go ahead and get started. So our agenda today, we're going to really quickly recap that Bayes' Theorem formula, and then we're going to get straight into a practice problem with diagnostic testing. So the formula is based off of conditional probability. It answers the question, what is the probability event A has happened given that event B has already occurred? So this pipe right here is called given, right? That's how we say it. So it's the probability of A given B. This formula on the left-hand side, you get out a posterior probability. I always remember this because it's the answer you get back, and posterior means the back, set equal to the likelihood, which is just the opposite of the posterior probability. So the posterior probability is the probability of A given B, and the likelihood is the probability of B given A. So we see that this is the opposite of the posterior. That is then multiplied by the prior knowledge that you have. A lot of times this is given to you, or you can look at the data set to get this answer. Both of these values are single numbers. And that's divided by the probability of event B. And most of the time, there are two scenarios in which event B can happen, and you want to make sure you capture both. So that was a quick recap of the formula. Like I said, part 1 goes into more details. Let's get right into an example. So 1% of the population has a disease. That is the prior knowledge that I'm giving you. The diagnostic test is accurate 97% of the time. Given that I have a positive test, what is the probability I actually have the disease? That keyword given means that we're working with that conditional probability. So since 1% of the population has the disease, I can calculate the probability of having the disease and the probability of not having the disease. So if the probability of having the disease is 1%, denoted by the decimal 0.01, that means the probability that the population doesn't have the disease is 0.99. But what does this accurate test mean? So there's two scenarios in which I can be accurate. I can have the disease and test positive. That is an accurate test result. So this would happen 97% of the time, given that I actually have the disease. And it's also accurate that if I don't have the disease and test negative, that would be our true negative. And this would also happen 97% of the time. So let's actually draw this out or visually look at this. So let's start with disease versus no disease. If I have the disease, there are two scenarios. I can either test positive or I can test negative. And this is the same if I don't have the disease. So let's actually fill in those numbers. Let's start with the disease. So there's a 1% chance I have the disease. I'm putting the 0.01 above disease. And there is a 99% chance that I don't have the disease. If I'm looking at an accurate test, I said that my test was 97% accurate. And so for someone who has a disease, a positive result would be an accurate result. So I get the 97% on my positive side. And on my negative side, I get 3% because my probabilities have to add up to 1. So this is going to be very similar for if I don't have the disease, but now I see that my numbers have flipped. Because if I don't have the disease, an accurate test would be a negative test, and that would happen 97% of the time. But an inaccurate test would happen 3% of the time. So this is how I can actually visually see what's going on. Now let's actually take that and apply that to our Bayes theorem formula. So once again, the Bayes theorem formula is up at the top, but we actually drew out exactly what we're looking for. So my question was, given that I have a positive test, so that is going to be on the right-hand side right here, what is the probability I actually have the disease, which is now on the left-hand side. So I'm trying to solve for the probability of having the disease given that I test positive. That's going to be equal to the likelihood, which is going to be the opposite. So that is the probability given that I have the disease that I test positive times the probability I have the disease divided by the probability that I test positive. And there are two scenarios that I can test positive. So let's fill in these numbers. So the probability given that I have the disease that I test positive is going to be the 0.97 that I see in my tree diagram. So given that I have the disease, I'm going to test positive 97% of the time. That is one single number. I'm going to multiply that by the probability I have the disease in the first place, which is denoted by this red circle here, which is 1%. I then am going to divide that by the probability I get a positive test. Now, I can either get a positive test if I have the disease, or I can get a positive test if I don't have the disease. So I'm going to make sure I capture both of these scenarios. So in this case, it is going to be 0.97 multiplied by 0.01 plus 0.99 multiplied by 0.03. And that is going to be what my denominator is. So I like to circle what I'm going to multiply on my tree diagram and then put a plus sign to remind myself that there's a plus in the middle. From there, I can get a test result, and that is going to equal out to 24.6%. So given that I have a positive test, what is the probability I actually have the disease? That is about 25%. So thank you all for tuning in with Learning with Jelly. Please like, comment, and subscribe, and I'll see you on the next video.